Okay, sir. I hope my screen is visible to you. Okay, then I'll start.
Yes, sir. Yes, sir.
Uh, Welcome. So this is the 12th session for the polymer process engineering, and this is the problem solving session. So we'll start from the first question. What is gutta percha primarily used for in dentistry? So gutta percha is one of the chemicals, one of the polymers which is being used in the industry. So we have four options here: filling material, teeth whitening, orthodontic brackets, and dental implants. So gutta percha is a what should I say now, isomer for the isoprene, and it's a variant of that itself. So we can see that image right here. Isoprene monomer, we have the gutta percha and the natural rubber polymer polyisoprene, and gutta percha is trans polyisoprene. So it is in the same family as the isoprene. So gutta percha is basically used as a filling material. So you can see right here how it is used as a filling material. So if you have a damaged tooth like this, which has an abscess and a root canal, we first dig out the entire part and then we fill and clean with the gutta percha inside it, as you can see in the last image, and then a crown is placed. Why gutta percha is used is because, first of all, it has minimal toxicity. So basically, it won't be infecting your gums or the surrounding teeth anymore. So it has minimal toxicity and it can be easily manipulated. Manipulated in the sense that it can be easily molded since it's isoprene based polymer. So it can be easily manipulated and molded. The shape can be changed easily. That is one part. And the one of the main points is that the removal can be done easily by heating or by using specific solvents which will either dissolve it or by heating itself, which we can remove it that way. So that is one of the advantages of that. Moving on to the next question. Which of the following is a common application of Serlin? So first of all, what is Serlin? Serlin is actually an ethylene ionomer. So you can see right here, the Serlin structure right here has been given. CH2, CH2, X, CH2C, and on one side we have the CH3 group, and on the other side we have COOM plus. That is the ionic group, where the M plus is the sodium, zinc, or potassium. Anyone it can be, and this itself is a repeating group. Now, what is so you can clearly see that it is based on the ethylene monomer. You can see that ethylene is present right here, correct? So uh, here it's like a it's not an exactly a polymer, it's an ionomer. What is an ionomer? Ionomer are composed of repeat units of both electrically neutral repeating units and ionized units, which are covalently bonded to the polymer backbone. So you can see right here, these are bonded to the polymer backbone. Uh, as we know that the primary forces which are present right here inside it are the ones which are holding on to the primary backbone, and these are present and these are connected by covalent bonding to the primary backbone. And as you can see, the ionic group right here, this is present as a pendant group. Now, what is pendant group? You can clearly see that the ethylene monomer backbone is a straight chain. Okay, so these groups are sticking outside. So they are sticking out like a small pendant. So that's why they're called pendant group, and uh, they are connected covalently to the main ethylene polymer chain as a pendant group. Ionic or the electrically neutral repeating unit as a ionic group right here. So these Serlins are basically used most in the packaging film industry. So packaging, any kind of packaging required, we use uh, Serlin polymer. So this is the Serlin is the trade name, but ethylene ionomer, where the ions are composed of sodium, zinc, or potassium, are the main like description of the Serlin compound. So they are used in the packaging films. Next, we have a incorrect statement identification question. Which of the following is or are the incorrect statement for the commonly used polymers in sports equipment? So we have commonly used polymers in the sports equipment. We have mm, cyanoacrylate is a versatile adhesive used in various field industries such as industry, medicine, and household applications. Vectran, Vectran is a synthetic fiber composed of liquid crystal polymer. It is an aromatic polyester obtained through the polycondensation of 4-hydroxybenzoic acid and 6-hydroxynaphthalene 2-carboxylic acid. Gutta percha is a polyterpene and a trans isomer of polyisoprene, and serline is a polyterpene and a trans isomer of polyisoprene. So these are the questions here. So amongst these, we have to find out which is the incorrect statement. So first one we have cyanoacrylate is a versatile adhesive used in various fields such as uh, industry, medicine, and household application. This is true. Cyanoacrylate is a very well-known adhesive material which is used in various places. Medicine, household application are only some of them. Then Vectran is a synthetic fiber composed of liquid crystal polymer. Yes, Vectran is a liquid crystal polymer, and it is coming from the same family as the Kevlar, or you can say polyaramides, polyaromatic aramide. It is an aromatic polyester. You can see right here, aromatic polyester obtained through the polycondensation of 4-hydroxybenzoic acid and 6-hydroxynaphthalene 2-carboxylic acid. So these are the ones which make the vector. So this is true. Then gutta percha is a polyterpene and trans isomer of polyisoprene. We have just seen in the previous question, and you can see right here that gutta percha is the trans isomer of polyisoprene. Isoprene monomer is there in gutta percha, and polyisoprene cis natural rubber is also present in this description. Then last is serline is a polyterpene and trans isomer of polyisoprene. Now we have already seen the description for serline and how it's an ethylene ionomer. So clearly this statement is false. Serline is a polyterpene and trans isomer of polyisoprene is the false statement or the incorrect one. So this is the answer for this. And last one we have fill in the blank and type uh, fill in the blank type question. We have polyolefins have dash to the most common solvents. So basically only two choices are right here. So first one is excellent chemical resistance, and that is the correct answer. That polyolefins basically have very good resistance to any kind of chemical attack on them. And why is that? As you can see right here, for an example, I have shown the ethylene polymer, that is the polyethylene. And you can see that uh, the carbon-carbon backbone, polymer backbone, which is present, and the hydrogens which are attached to it, you can clearly see there is no steric hindrance or any kind of pendant group which can cause any kind of steric hindrance in the polymer chain itself. And there are no functional groups present for any kind of chemical to attack the polymer or the polymer product with which you are using it. Okay. So any kind of chemical attack is very rare on polyolefins, and they are able to withstand, and they are inert to many of the chemical as for example acids and bases. They don't affect the polyolefins as much, and polypropylene and polyethylene are very commonly used for sealants or any kind of caps for the uh, acid acid containers or anything like that. So mild, any kind of mild acid attack or basic attack, easily it can handle. So that's why it's chemically inert. Since they do not have any functional groups present in their backbone, which can react to the acid or bases. Next, we have which of the following is incorrect for polyurethanes, that is PUs. PUs are the polymers that contain carbamate group in their molecular backbone. First one is that. So we have the entire structure for how the polyurethanes are made. Firstly, polyol is mixed. Polyol is added to the diisocyanate, and you can see that that itself gives you the polyurethane. And you can clearly see the R O C double bond O N H or NH or any kind of R or R dash. That group is called the carbamate group. So PU polymers that contain carbamate groups in their molecular backbone. So definitely, carbamate group is contained inside the polyurethane backbone. So yes, polyurethanes do have the carbamate group. So first statement is correct. Then, and mind you, in this question we have to find the incorrect answer. So PUs have applications in fields of insulation, surface coating, adhesives, and solid plastics. So clearly from the previous classes, we already know that polyurethanes are used in conformal coatings in electronics industry, especially for the surface coating. Uh, so that's why insulation, surface coating are definitely the fields of application for PU. True. The reaction between diisocyanate and polyol groups form PUs. You can clearly see that is happening right here. The last one is the process for synthesis of isocyanate-based polyurethane is green and non-hazardous in nature. This is false because the diisocyanates and polyurethanes are not exactly environment friendly and they are hazardous in nature. That's why the synthesis process of isocyanate-based polyurethanes are quite, what should I say now, hazardous. And they are not exactly green processes. So that's why the last statement is incorrect, and that is the answer for this question. Then we have choose the correct option one. Statement one says tenacity is the stress at which the fiber breaks, expressed in grams per denier. In statement two, we have the elongation at break, EB, measures the fiber's extensibility and ability to stretch before breaking. Okay. Then the last one is the elongation at break EB of textile fibers depends on the stretching and drawing of fiber and heat setting at the end of fiber making process. Now we'll analyze the statements one by one. Statement one is the tenacity is the stress at which the fiber breaks, expressed in grams per denier. This is correct. So if you were to look at any kind of stress strain diagram for any of the materials, so one second. So if we were to take a look at the stress strain diagrams. So here we have the stress and here we have the strain. So starting from zero. So the material when it breaks right here, right? This portion is the this elongation which you see right here. This is the elongation at break. This exact elongation at which it is breaking, and the values are coming back to zero. The values of stress, which the material is able to take, that is called the elongation at break. Now, what is the tenacity? Tenacity is the stress at which the fiber. The representation which I've shown right here is not exactly correct. It's just a rough diagram. So for fibers, uh, the the graph can look something like this. It will just go like a straight line, and then it will suddenly break. It will snap. So yes, the maximum stress is the stress at maximum stress, or the tenacity is the stress at which the fiber breaks, expressed in grams per denier. Yes, denier is per 9,000 meters. What is the weight of the fiber? And for uh, every gram of that, how much stress it is able to take, that is being expressed by the tenacity. Tenacity is the term used for that. So statement one is true. Then second statement is the elongation at break measures the fiber's extensibility and ability to stretch before breaking. So as I said, the x-axis is the strain or the elongation. So you can clearly see the change in length which is occurring as the material is taking stress. So when it goes to the final position where it breaks, that is the elongation at break. So statement two is also true. In statement three, we have the elongation at break EB of textile fibers depends on the stretching and drawing of the fiber and heat setting at the end of fiber making process. Now, when you are manufacturing a fiber, the way you pull and cool down the fiber actually makes up a lot of the interior structure of the fiber itself because polymer processing polymer processing actually affects the properties of the polymer to a very large extent. So if the pulling or the spinning or stretching or the drawing of the fiber, right? If it is done properly, the polymer molecules inside the fiber can be arranged into a very crystalline manner, which will make the fibers very strong. So the elongation and break of that textile fiber will be very good. So definitely, it is very much dependent on the stretching and drawing of the fiber, and that can only be done at a particular heat setting. If the fiber is actually very hot or the polymer is actually very molten in nature, extensive stretching or drawing will just make it very weaker. So any particular heat setting is required at which the stretching or drawing of the fiber can be done to bring out the like what should I say, the maximum mechanical properties of the fiber. So elongation and break is very important. So that's why it is definitely dependent on the stretching and drawing of the fiber and the heat setting. Stretching and drawing of the fiber in the heat setting. So that's why statement number three is true. So all statements one, two, and three are correct. For the new students which have joined just now, I will start again from the beginning. Uh, First question is, what is gutta percha primarily used for in the dentistry industry? So we have been given four options here: filling material, teeth whitening, orthodontic brackets, and dental implants. So we have the gutta percha's chemical structure right here. You can see right here the gutta percha. Actually a trans isomer of the. You can see right here it's a trans polyisoprene. So you can clearly see it is from the rubber monomer itself, isoprene, and the gutta percha is the trans polyisoprene of the isoprene monomer. So where is it used? So you can see right here, it is used as a filling material. So you can see that how the infected tooth is filled with the gutta percha. The root and the canal are first of all drilled open and cleaned, and after that gutta percha is filled into it and the crown is applied. So why gutta percha is used is because first of all it has so first of all gutta percha is a very less in toxicity. So since it's less in toxicity, it won't be able to affect the surrounding teeth, or it will not further cause any kind of damage in the gums itself. So that's why gutta percha is used. Then ease of changing the shape or moldability or manipulation, we can say that it can be easily molded right away, and we can change the shape and however we want to fill it inside the canal or the root near the roots. So that also gives it a great degree of flexibility. And then we have ease of removal by using heat or any kind of solvent. So if there is any kind of problems or if the filling is needed to be replaced again, it can be easily removed by using some solvents or heat treatment itself. So that's what makes the gutta percha another good candidate for the filling material. Next question: which of the following is a common application of Serline? So first of all, what is Serline? So Serline right here has been given. It's an ethylene ionomer. I will explain what is an ionomer in a minute. You can see right here how the ethylene monomer CH2 is present, and connected to that is a CH2 C bond CH3 and C double bond O M plus. Now this M plus is the ionic group which can be composed of either sodium, zinc or potassium. So these are used in the Serline. And Serline is an ethylene monomer, ionomer. So what is an ionomer? Ionomers are composed of repeat units of both electrically neutral repeating units and ionized units which are covalently bonded to the backbone of the polymer itself. So you can see right here, since it's an ethylene ionomer, the ethylene backbone group which is present right here is uh, present right here in the covalently bonded section. So you can see they are present as covalently bonded section as a pendant group. So you can clearly see that it is present as a covalently bonded pendant group C double bond O M plus. So these are bonded to the polymer backbone itself. Now, the most common application of Serlin is basically in the packaging films and packaging film industry. So, many of the packagings are made using the Serlin polymer. So, because uh, it is having the properties which are actually very useful in the packaging industry, and that's why Serlin is a good candidate for that. Which of the following is are the incorrect statements for commonly used polymers? So we have four options right here. First is the cyanoacrylate. Uh, Cyanoacrylate is a versatile adhesive and used in the various fields in uh, industries, medicine, and household applications. So cyanoacrylate is it's a kind of an adhesive, or it's actually kind of like a super glue, which will it's defined as a quick bonding adhesive also, and it will combine anything from metal to plastics. So that's why it is very versatile and can be used anywhere in any kind of industry, and that's how it finds its applications everywhere. So this statement is true. Next, we have the Vectran. Vectran is actually it comes under the family of a aromatic polymers, and Vectran is in the same class as the aramides, Twaron, Nomex, because it is also used in defense industry quite a lot. But because of its low resistance to UV radiation and other properties, it is not as extensively used as Kevlar. So that's why Vectran is a synthetic fiber composed of liquid crystal polymer, just like Kevlar, and it is an aromatic polyester obtained through polycondensation of 4-hydroxybenzoic acid and 6-hydroxynaphthalene 2-carboxylic acid. So this is true. That is the base monomer for formation of the Vectran, which is a aromatic polyester and formed through the polycondensation polymerization. So this statement is also true. And third one is gutta percha is a polyterpene and a trans isomer of polyisoprene. So just now here we can see in the illustration itself that isoprene monomer is there. And if we were to check the repeating units of the gutta percha, we can clearly see that it is the trans polyisoprene and it's a trans isomer of the polyisoprene. So that statement is also true. That brings us to the last statement of serline is a polyterpene and a trans isomer of polyisoprene. Now, from the previous question itself, we already know it's an ethylene ionomer. So we have checked that. So serline is not a polyterpene and it is not a trans isomer of polyisoprene because trans isomer of polyisoprene is gutta percha. That's why the last statement is incorrect, and this is the answer for this question. Then we have the fill in the blanks. Uh, Polyolefins have dash to most common solvents. So, what is the property amongst these two options? The first one is excellent chemical resistance. So, definitely, polyolefins have excellent chemical resistance to any of the common solvents. And why is that? It's because, first of all, you can see the example right here. This is the ethylene, so polyethylene. And another example would be polypropylene. These two are very popular polyolefins, and the reason why they are able to exhibit such high chemical resistance is because you can clearly see in the polymer backbone itself that there are no pendant groups or there are no kind of moieties present or the functional groups which can interact with any of the external solvents which will be trying to enter or attack the polymer molecule. So that's why there is no interaction itself, and that is the exact reason why polyolefins are not very inert in nature with respect to any kind of chemical attack on them. So that's why they have excellent chemical resistance. Next, we have which of the following is incorrect for polyurethanes, PUs? PUs are polymers that contain carbamate group in their molecular backbone. So here we have the illustration for polyols and diisocyanate, which forms the polyurethane. And you can see on the bottom that group is called the carbamate group. So that carbamate group, you can clearly see that it is found in the backbone of the polyurethane molecule itself. So you can see RO, C double bond O, N and H with R dash clearly present inside the backbone of the polyurethane monomer. So molecular backbone already carbamate is present. So first statement is true. Second statement, PUs have applications in fields of insulation, surface coating, adhesives, solid plastics, flexible and hard foam, etc. This is also true. We have already seen in the previous classes that insulation, surface coating, and adhesives, PUs are widely used in those fields. And since PUs are also used in the conformal coatings of the PCBs, printed circuit boards, for prevention of any kind of dust or any kind of moisture to seep into the PCBs. So yes, definitely, PUs have application in these fields. So this statement is also true. Third one is the reaction between diisocyanate and polyols form groups form the PUs. So yes, definitely, we can see the reaction scheme. The polyol and the diisocyanate are combined together to form the polyurethane. So definitely that is happening. So third statement is also true. Then last one we have the process for synthesis of isocyanate-based polyurethanes is green and non-hazardous in nature. This statement is false because already we can see that isocyanate is quite hazardous in nature, and the entire process and the byproducts which are formed during this synthesis are not exactly environmental friendly. So it is not a green process, and it is quite hazardous. So that's what makes this process not green, and that's why fourth option is the incorrect one. And last question we have, statement one. Choose the correct option of the following statement. So statement one we have tenacity is the stress at which the fiber breaks, expressed in grams per denier. Statement two, the elongation at break EB means the fiber's extensibility and ability to stretch before breaking. In statement three, the elongation and break of textile fibers depends on the stretching and drawing of the fiber and heat setting at the end of fiber making process. So we'll take a look at the statements one by one. So first one we have tenacity is the stress at which the fiber breaks. So here we have a stress strain diagram. So you can see that we have the strain on the x-axis and stress on the y-axis. So clearly for any material, just for a description sake, I have shown a curve which goes on like this and then it stops right here and then it collapses. So clearly the tenacity is the stress, the total stress at breaking. So you can see that once the point at which it breaks, so this point right here, right? So the stress at this point is exactly where the fiber will break and it is expressed in grams per denier. So yes, statement one is true. In statement two, we have the elongation at break, EB, measures the fiber's extensibility and ability to stretch before breaking. So we can see the elongation or the strain in the material. Strain is basically the change in dimension of the material. That is del L by L. So change in length by L, the original length. So we can see how the material is stretching to a different dimension and then it breaks. So that is the elongation at break. So measures the fiber's extensibility and ability to stretch before breaking. So that this statement is also true. So this statement is also true. And then statement three, we have the elongation and break EB of textile fibers depends on the stretching and drawing of the fiber and heat setting at the end of the fiber making process. So definitely the elongation and break of a textile fiber depends upon the stretching and drawing because, for example, when you are processing the molten polymer, what happens is when you start stretching it, the molecular arrangement of the polymer backbone inside the fiber itself will start reorienting. That's why polymer processing has a huge impact on the properties of the polymer itself. So, as the stretching and drawing of the fiber takes place, the polymer molecules, right, they arrange themselves in a crystalline manner, and that is the exact reason why the elongation and break will be influenced in that manner for that particular fiber. So statement three is also true. So taking a look at them, look at these three again. Tenacity is the stress at which the fiber breaks. True. The elongation at break measures the fiber's extensibility and ability to stretch before breaking. So that can be depicted in the stress strain curve itself. From the original length to the change length, del L by L, the strain or the elongation at break. This is the point where the material breaks. So we can clearly see that this statement is also true. And just as I explained, the third one is also true. So all statements 1, 2, and 3 are correct. So these three are right. So that is the third option. So for anyone who has joined just now, I'll start repeating the questions from beginning again. So first question is, what is gutta percha primarily used for in dentistry? So we have four options right here: filling material, teeth whitening, orthodontic brackets, and dental implants. So gutta percha's molecule has been shown right here, and gutta percha is primarily used in the dentistry for the filling material as a filling material. Now, what is a filling material? So you can clearly see right here, whenever the tooth is decayed from inside, we drill an opening and clean it, and then we fill it with the filler material. So right here in this case is the gutta percha. So why do we use gutta percha in this industry? Is because first of all, it has minimal toxicity, so it reduces any kind of risk to the surrounding teeth that it won't decay any of them further. So minimal toxicity. Then we have the ease of manipulation, or you can change the shaping and other parameters of that are very extensively easy when trying to fit the gutta percha inside the root. And then the ease of removal with heat or solvents. So easily you can apply heat or solvents to remove the filler material from there. So that is one of the few advantages of the gutta percha, which are primarily used in the dentistry for the filling material. Then we have which of the following is a common application of the Serlin. So Serlin molecule, what is Serlin first of all? So Serlin is shown right here. Uh, Serlin is actually a ethylene ionomer, and I will explain in a minute what is an ionomer. So you can clearly see the illustration here. So the Serlin is a uh, so you can see right here that the Serlin molecule has been shown here. And this Serlin molecule has the CH2 group, which is the ethylene group. And in the similar backbone, you can see CH2 is attached to C, where we have two covalently bonded, one CH3 molecule and one C double bond O N plus sodium, zinc, or potassium molecule. So, Serlin is a material which is widely used for cosmetic packaging industry. So that's why packaging films are the answer for this question. And then it is characterized with above average transparency and resistance to mechanical damage and lower mass compared to glass, which is commonly used. So that's why Serlin is preferred over them. So what is an ionomer? Ionomer is actually composed of a repeat unit of both electrically neutral repeating units and ionized units, which you can see right here, electrically neutral and ionized units, which are covalently bonded to the polymer backbone itself. So you can see the ethylene backbone, these are covalently bonded and they are present here as a pendant group. So pendant groups are the groups which are sticking out from the polymer backbone as it is. As you can see, it's a single ionized moiety or a functional group. So that is the exact reason why it's called a pendant group. And if it were present as a branch, or if any other repeating unit, any other more repeating units were there, then it would have been called a branching group, not a pendant. So this ionized group is present as a pendant group. So Serlin is used as a package. Serlin is used in the packaging film industry. Which of the following is are the incorrect statement for the commonly used polymers? So we have a few options right here. First is cyanoacrylate is a versatile adhesive used in the various fields such as industry, medicine, household, and applications. Yes, cyanoacrylate is very popularly used, and it is also called the super glue. So cyanoacrylate is actually used in many of the household items, and it is actually used in medicine industry and any other strong bonding. If you want, you can use cyanoacrylate, and these cyanoacrylates are like very good at bonding metal to metal or metal to wood also. So that's why these adhesives are really good and they find their applications in these industries. So first statement is true. Next we have Vectran is a synthetic fiber composed of liquid crystal polymer. So liquid crystal polymer are a class of polymers and the Vectran is a part of it, similar to Kevlar, and they both are used in the similar defense industry for making fibrous armors or the fabric, the bulletproof fabrics for the soft armors. Another thing is that it is an aromatic polyester obtained through polycondensation of hydroxybenzoic acid and hydroxynaphthalene carboxylic acid. So similar to Kevlar, it's a condensation polymer, and you can see right here that it is obtained through the condensation of hydroxybenzoic acid and naphthalene carboxylic acid. So this statement is also true. So first two statements are true. And third one is gutta percha is a polyterpene and a trans isomer of polyisoprene. So we have seen in the we have seen the gutta percha in the first question, and again right here we can see the isoprene monomer which is present in the illustration, and the gutta percha is a trans polyisoprene of the similar isoprene monomer. So you can see that it's definitely a trans isomer of polyisoprene. So this statement is also true. The last one is serline is a polyterpene and a trans isomer of polyisoprene. So clearly, we have seen in the previous question that serline is actually a ethylene ionomer. So it's not a polyterpene and it's not of the family of isoprene. So definitely, last statement is incorrect. So the last one is the false statement. Next, we have fill in the blanks. Uh, Polyolefins have dash to the most common solvents. So we have two options right here: excellent chemical resistance and poor chemical resistance. So one of the examples which I've used right here is the ethylene or the polyethylene. And similarly, in a similar vein, you can use polypropylene also. So clearly, polyethylene, you can see that there are no other functional groups present, and only the polymer backbone with the hydrogen on either sides are existing. So what does this do is that it makes the polymer backbone or the entire polymer itself quite stable because there are no functional groups present on which the solvents can attack. So that makes the entire material extremely inert to any kind of external attack of the chemicals. So that's why polyolefins like the polyethylene and polypropylene are quite inert to any kind of chemical attack, and that's why they have excellent chemical resistance because they do not have any kind of functional groups present right there, which can be influenced by the solvents. Which of the following is incorrect for the polyurethanes? So first is polyurethanes are polymers that contain carbamate groups in their polymer backbone. So here we have the illustration of a polyurethane group, polyurethane polymer with the monomer and the monomer or the repeating unit right here. So you can see clearly see in the repeating unit the R O C double bond O and N R R3 and R2, which is present right here. This repeating unit is what is called the carbamate group. So carbamate groups are definitely part of the polyurethane. So first statement is true. Second statement, polyurethanes have applications in fields of insulation, surface coating, adhesives, and solid plastics. So yes, polyurethanes do have a very extensive application in the surface coating industry, and in the electrical industry also conformal coatings are made using the polyurethanes, and these coatings make sure that humid environment or any kind of corrosion does not take place on the printed circuit board, and that is the exact reason why polyurethanes are used on that. So second statement is also true. Third one we have the reaction between so third one we have the reaction between the third one is the reaction between diisocyanate and polyols group forms the PUs. So you can see clearly right here that polyol and the diisocyanate react together to form the polyurethane. So we have the soft segment and the hard segment combined together to get the polyurethane. So this statement is also true. Then last one, we have the process for synthesis of isocyanate-based polyurethanes is green and non-hazardous in nature. So uh, this statement is actually false because the byproducts which are released during the polyol or the diisocyanate formation, diisocyanate uh, addition to form the polyurethane are not exactly green in nature and they are harmful to the environment. That is the exact reason why the last statement is incorrect. And the last question, choose the correct option for the following statements. So first is tenacity is the stress at which the fiber breaks. So we have the stress strain diagram right here. We have the strain and the stress, and you can clearly see as the material deforms, it starts taking stress, and then it breaks at one point. So tenacity is the stress at which the material or the fiber breaks. So you can see right here that first statement is true. And second, we have elongation at break measures the fiber's extensibility and ability to stretch before breaking. So definitely the change in dimension or the change in length of the fiber you can see. That is the strain. Strain is nothing but the change in dimension del L by the original length L. So that measures the fiber's extensibility and ability to stretch before breaking. So yes, right here it breaks off. So before breaking, so this definition also suits the statement two. Then statement three is elongation and break of textile fibers depends on stretching and drawing of fiber and heat setting at the end of the fiber making process. Again, uh, the stretching and drawing of the fiber draws the polymer molecules into a more crystalline arrangement, making the fibers more stronger. And that can be only achieved at particular heat settings because we do not want the polymer to be too rigid or too soft. And the stretching or the drawing should be done at a particular heat setting. So that again is true. So all statements 1, 2, and 3 are correct. So this actually this video will be uploaded on the YouTube, so you can take a look there also again if you want to revise again through these questions. And next week again, I will take a class. It will be like an extra class, and I will be going through um, I will be going through all the previous assignment questions also, and we will be discussing few of them from starting from assignment one. So it will be like a recap class just before your test, which will be, I guess, in the following week. So if you want me to explain this again, you can just ask me. If you have no more doubts, today's class is over. Any of the recaps you want to see, you can see it right there on the.
Sir, can you go just rush through the slides? I was a bit late, sir. Just rush
Yeah,
through.
yeah.
Rush.
Yeah, sure, sure. So the first one right here is the what is the use of gutta percha in the dentistry industry? So we have four options right here. So the answer for this is the filling material. So how it is filled right here, it is shown. And gutta percha is basically used because of its minimal toxicity, its ease of manipulation, and the ease of manipulation and ease of removal using these solvents and heat. So that's what makes it an excellent candidate for used as a filler material for the dentistry industry. Then we have which of the following is a common application for Serlin. So Serlin is used as cosmetic packaging in the packaging industry. So packaging films are made using this. And you can see right here, Serlin is an actually ethylene ionomer. So you can see CH2CH2, that is the ethylene backbone. And you can see right here that the pendant group is present as a ionic group that is COO N plus. And this N plus can be sodium, zinc, or potassium. And this ionomer is composed of repeat unit of both electrically neutral, that is the CH3, and uh, ionically ionic unit, that is the C double bond O M plus, which are uh, you know exactly covalently bonded to the carbon atom right here. So that is what makes it a ionomer. So the CH2 group is your electrically neutral one, and the C double bond O is the ion which forms the ionic part of the monomer, are the repeating units in the Serling, and they are used in the packaging film industry. Then which of the following is or are the incorrect statements for commonly used polymers? So first of all, cyanoacrylate is versatile adhesive used in various fields such as industry, medicine, and household. So definitely cyanoacrylate is used as a super glue, and it is able to stick or it is able to be used as an adhesive with many of the extensive materials such as metals, wood, and any other material. So yes, first statement is true. Second one is Vectran is a synthetic fiber composed of liquid crystal polymer, which falls in the same liquid crystal polymer category of the Kevlar also, and they both are used in the defense industry. Kevlar is used more extensively than Vectran, first of all. Then on top of that, it's an aromatic polyester. Uh, Kevlar is a polyaramide, so aromatic. So it's a aromatic, and then aromatic polyester obtained through the polycondensation of 4-hydroxy benzoic acid and 6-hydroxy naphthalene 2-carboxylic acid. So this description for Vectran is also true. Then third one we have gutta percha is a polyterpene and a trans isomer of polyisoprene. So here is an illustration of the gutta percha right here. We can see that the isoprene monomer, uh, the natural rubber, which is the cis polyisoprene, and the trans polyisoprene is the gutta percha. So this statement for that is also true. Then the last one is serline is a polyterpene and a trans isomer of polyisoprene. Now this description does not match that of the serline which we just studied in the previous question. Serline is an ethylene ionomer, so this statement is false. Then polyolefins have dash to most common solvents. So the correct answer for this is excellent chemical resistance. And that is because they do not have any pendant groups or any external, any outlying functional groups which can be attacked by the solvents. So that's why they have excellent chemical resistance. Then polyurethanes, what is incorrect for polyurethanes? So polyurethanes are polymers that contain carbamate group. So we can see that the carbamate group is right there down. So that is a part of the polyurethane molecule itself. So it forms the part of the molecular backbone. And polyurethanes have applications in fields of insulation, surface coating. Clearly, we have seen in the last class also that polyurethanes are used in conformal coating, and they are definitely used for surface coating and adhesives also. So first two statements are true. And third one is the reaction between diisocyanate and polyol groups forms PUs. So the reaction scheme is shown right here. Polyiol and diisocyanate combine to give you a polyurethane. The process for synthesis of isocyanate-based polyurethanes is green and non-hazardous. This is not true because the byproducts formed during this synthesis process are not exactly green in nature, and they cause harm to the environment. So the last statement is incorrect for the polyurethanes. And the last question, you have already taken a look at it. So yeah, that's all for this class. I will be taking a recap class next week, and you can join at that time. So we will be going through many of the questions from the previous assignment. So if you have any doubts, you can ask me during that time.
So any question patterns for the exams will be given, sir, or any assignment like that, prioritizing the questions or something like that?
We will be going through recap of all the assignments itself. Uh, Definitely, like the exam pattern will be multiple choice questions only, and not exactly like it's that important. The exam pattern. It would be, I would say that it would be fairly viable to do it in a limited amount of time. So yeah, we will be only going through a recap of the previous assignments. Thank you for attending the class. You can find the video for this on YouTube. This will be uploaded soon. Thank you.